Alright, so I'm going to be reviewing in this video the multiple choice questions for the January 2012 paper, and I'm going to look specifically at the questions to do with circular motion, gravity, electric fields and capacitors. Okay, so let's start off with question 4, which is the first one on that. So looking at some circular motion, so what is the centripetal force on a small object of mass m on the perimeter of the disk? So first of all, to get the force, we would need the mass of the object, the angular speed of the object, and the radius. So we've got mass, and then that's going to be 2 pi f in terms of the frequency, squared, multiplied by d over 2 in terms of turn the diameter and the radius. So we're going to end up with 2 pi squared f squared d, which is this one. So that one is going to be C. Alright, so let's move on to the next question. Alright, so moving on to the next question. So Newton's law of gravitation explains A, the origin of gravitational forces. No, total rubbish. That's not true. Why a satellite burns up. No, it's nothing to do with burning. Why projectiles maintain a uniform horizontal speed. Yeah, that seems sensible. How various factors affect the gravitational force between two particles. Yeah, that is exactly what it is. Yeah, that's what the essentially is for, because remember Newton's gravitation is essentially like this equation here, so you're looking at two different objects and it expresses the force between them. So yeah, that's exactly what the law of gravitation is doing. Okay, if an electron and a proton are separated by a distance of 5 times 10 to the 11 meters, what is the approximate gravitational force of attraction between them? So we're going to be using that equation here. So we would use 6.67 times 10 to the minus 11 times the mass of a proton times the mass of an electron divided by the distance between them squared. And if we calculate that, we end up with a number which is approximately this one. So it's a tiny, tiny force of gravity, which is why we never consider them when we're dealing with the atomic structure and that kind of thing. Okay, so let's have a look at question 11. So a spherical planet of uniform density has a radius r. Which line A to D gives the correct expression for the mass and the gravitational field strength at the surface? So the volume of a sphere is 4 over 3 pi r cubed. And then in terms of so mass would be your density times volume, so it's going to be 4 over 3 pi r cubed times by the density. So which lines would that apply to? So we can already eliminate A because it's got r squared, not r cubed. Same for C, it's got r squared, not r cubed. And so it could be either B or D at this point because they both give the correct answer we've got there. So looking at gravitational field strength at the surface, so E is equal to Gm over r squared. So that's going to be G times this expression, density, divided by r squared. So that's going to cancel with the cubed, just leaving an r. So we're looking for G 4 pi r, which is this one here, so not B. We've lost the r term, so that one would not be correct. Alright, so let's move on. Okay, so gravitational potential at the surface of Earth of radius r is V. What is the gravitational at a point r above the Earth's surface. So remember how we calculate potential? It's minus gm over r. The new potential, we've replaced r by 2r, so it would just be, because that's the distance of r plus r, which is equal to v over 2. So that's going to be b. So looking at 13, a satellite is in orbit above the surface of a planet with mass m and radius r. What is the velocity of the satellite? So this is going to be talking about a geosynchronous one, where gmm over r squared is going to be mv squared over r. Cancel your m's, cancel r squared, so v squared is gm over the radius distance, which would be r plus h, because it's h above the surface. So that would give you v is going to be the square root of gm over r plus h, which is expression A. So the key thing here is for the radius in the force equation and the circular motion equation, it would need to be the radius of Earth plus the height above the Earth's surface, essentially. So that's why you should have r plus h. Okay, so let's scroll down. So we've got a repulsive force F acting between two positive point charges separated by a distance r. What will be the force between them if each charge is doubled and the distance between them is halved? So we've got a force, which we can calculate using this equation here. So essentially, if both charges are doubled, we essentially multiply each term by 2, so the top line's been multiplied by 4. Distance between them is halved, so this r is going to be divided by 2, which means this r squared term is going to be a quarter of what it was before, which means we're going to have 4 divided by a quarter, which is 16. So it's going to be 16 times as big as it was before, or answer D. Okay, so the distance between 2 point charges of 8.0 nanocoulombs and 2.0 nanocoulombs is 60 millimeters. At a point between the charges on the line joining, the resultant field strength is 0. How far is this point from the 8.0 nanocoulomb charge? Okay, so let's look at how we do the field strength. So Q over r squared, let's call it r1, so let's call that one q and this one little q, must be equal at that point to q over r2 squared. So this is, we could replace this big Q with 4 little q and then cancel out q's. So essentially what you'd end up with is the ratio of r2 squared over r1 squared is equal to 1 over 4. So then the r2 divided by r1 is a half. So essentially it's going to be twice, if we rearrange this, more useful. R1 is twice R2. So we're going to have a point here where this one would be 40 millimeters and this one would be 20. So we're satisfying that condition. So in terms of from the 8 coulomb charge, that's going to be 40. So it's going to be answer C. You'll notice that I skipped out all the constants because they would be on both sides and I'd cancel them anyway, so there's no point considering them in this question. Okay, so which one of the following could not be used as a unit for electric field strength? So field strength, the electric would be the newtons per coulomb of charge. So then we need to think what we could substitute in, so we could do newtons per amp second, because Q equals IT, so we could stick that in there. What else are we going to try? We can replace newtons by joules per meter, because remember, a force times distance is energy, so energy divided by distance. ASM, which is B, so that one can be used, so it can't be that one. And we could also have written that as joules per coulomb meter, so that would mean A is possible, so it's not going to be that one. Newtons per amp second, we've had that one, so then eliminating that, that would leave us with this one here. So the first three are possible by making substitutions using Q equals IT, and work done is force times distance essentially, and it will get answer D. Okay, so a capacitor stores a charge of 600 microcoulombs when charged to a potential difference of 6.0 volts. What would the potential difference across the plates be if the charge stored increases by 50%? Okay, so with capacitors, the potential difference is directly proportional to the charge. So essentially, if Q has been multiplied by 1.5, V would have to also be multiplied by 1.5, which is an increase of 50%. So the potential difference is 6 times 1.5 equals 9.0 volts. So it's going to be answer C there. This is like a relationship you just need to know, that the potential difference is directly proportional to the charge stored, and you can use that to solve this right here. Okay, so last few. We've got a graph shows the results of an experiment. So you've investigated the relationship between Q and the PD across it. So again, so like previously, we're showing they're directly proportional to each other because it's a straight line through the origin. Which one of them is not correct? Okay, so energy can be found by calculating the area under the line. So the area under this line would be essentially a triangle. So it's going to be a half QV, which is indeed a expression for the energy stored in a capacitor. So that is true, so A is not possible. If a capacitor or a smaller capacitance had been used, the gradient of the graph would be steeper. Let's think about this. So we've got this equation here, or to put it in y equals mx plus e for the graph that we've got, like this. So if capacitor was smaller, the 1 over capacitance would be a larger number, so the gradient would be steeper, so that's correct. If Q were doubled, the energy stored would be quadrupled. So if we remember, so energy, and what we're going to do is we're going to substitute in for V, so V equals Q over C, so you'd end up with Q squared over C. So if you doubled Q, you would indeed quadruple energy, so that's correct. The gradient graph is equal to the capacitance. No, total rubbish. The gradient is 1 over the capacitance, so that one is the one that's incorrect. A 10 microfarad capacitor is fully charged to a potential difference of 3.0 kilovolts. Energy stored in the capacitor can be used to lift a load of 5.0 kilograms to a vertical height h. What is the approximate height value of h? So we're going to think about changing energy, essentially. So the change in GPE is going to be that. And the energy stored in the capacitor is going to be a half CV squared. CV squared. So we can rearrange, so if we want H, it would just be a half CV squared over mg. So we can put in those values that we've got, so the 10 microfarads, 3.0 kilovolts on your top line squared, and then 5.0 and 9.8. And when you do that and put the numbers in, you will end up with this value down here. Alright, so those are all the questions I'm going to look at from the multiple choice section.